Welcome to NASA's Jet Propulsion Laboratory in Pasadena, California. I'm Veronica McGregor. We're here for another very exciting event that's going to take place just 5 days from now. We are attempting to land another mission on Mars. And this mission is like no other that we've sent to the Red Planet. This mission will be studying the deep interior of Mars to tell us more not only about Mars, but also about how all rocky planets formed, including the Earth. Our landing time is Monday, November 26th at about noon Pacific time, 3 p.m. Eastern time. And I want to give you some websites immediately because I want you to bookmark these so you come back on Monday and you watch the landing live from Mission Control. If nothing else today, please book nasa.gov/live or either one, go.nasa.gov/InSight Toolkit. The InSight Toolkit will have a link to multiple ways that you can watch on live, both on NASA and on social media channels, including a live feed from Mission Control in 360 degrees, so you can feel like you're sitting in there with the rest of the mission team. Our event today is going to be divided into two parts. We're going to spend the first hour talking with mission managers about how InSight will operate on the surface of Mars, and also tell us a little bit more about the white knuckle event that will take place Monday with entry, descent, and landing. Following that, we're going to have the science panel. That will start at 11 a.m. Pacific time, and they will describe how these instruments that we're going to place on the surface of Mars will be able to take the vital signs of the planet to tell us more about rocky planets. I'm going to start now by introducing our first guest, and it is Dr. Thomas Zurbuchen, and he is the NASA Associate Administrator for the Science Mission Directorate. Welcome.
Thank you so much. Hi, everybody. Well, I'm so excited to be here, and of course to recognize that InSight is part of the NASA science program. Over 100 missions exploring our planet, our star, the sun, planets elsewhere in the solar system, but also worlds well beyond our solar system, asking questions that are really hard, such as, where did we come from? Is there life elsewhere? With this program, with the many missions, we explore the secrets of the universe, and we enlarge the space we live and think in. With this program, we also protect and improve life on Earth. And we think of the many people that were affected by the catastrophes here at this coast, but also elsewhere on Earth, in which we have a direct impact in a positive fashion. And we're so glad about it. InSight will join these missions that you see up there at Mars. History, and please for the second visual, a history of exploration of this neighboring planet. Going to Mars is really hard. As humanity, the explorers all over the world, we're batting about 50% or less of successful missions there. The exciting part is here, though, we're building on the success of the best team that has ever landed on this planet, which is the NASA team with its contractors and its collaborators. InSight will join the missions that are out there that have since 1965 at the first flyby. And it will join missions that are already there roaming around the surface and flying around it. And of course you read that just a few days ago we actually announced where Mars 2020 will land on this exciting planet. And frankly, we're really looking forward to that, and also think beyond that as we go to the moon now and eventually to Mars with humans. We will, of course, take advantage of all the knowledge we're gaining right here with these robots that are there, and really teach us everything about this environment that we can then benefit from. Right now, everything is about InSight, though, because this exciting mission is on the way there, becoming an active mission on the surface. And the person who has most to do with this, frankly, is the project manager, Tom Hoffman. I'm now happy to introduce to the stage. Thank you so much.
Thank you very much, Thomas. I cannot express to you how excited I am to be standing up here today to talk with you. Just 5 days from us landing, my heart is beating inside of my chest like a drum. I've been working on this project for 7 years, and to be literally just 5 days from landing and starting to get the science that we've been working so hard for, to me is absolutely thrilling. I'm so excited I can't even express to you how excited I am. So we launched May 5th of this year from Vandenberg Air Force Base. We were the very first interplanetary launch ever from the West Coast, and being a West Coast guy, California native, very excited to break the monopoly that Florida has had on launches to other planets. So we've been journeying to Mars. We've gotten about 295 of the 301 million miles that we have to go. We've gone almost the 7 months that we need to go, just 5 days left. But we can't do that alone. We have been working with, really, as Thomas said, the very best partners across the globe for this mission. So if I can get the first graphic here, you can see we have domestic partners that largely built the spacecraft. You'll hear from Stu Spath coming up. Lockheed Martin is the main spacecraft vendor. We have components from many other domestic partners, but the instruments were all built largely by European partners. We have representatives of those that will be talking in the next talk. In addition to that, the science team is made up of people across the globe. So you've heard the expression, it takes a village to raise a child. It really takes the whole globe to build a breakthrough instrument like we have today with this InSight mission. So with that, I'd like to go to the next graphic. So we've been cruising to Mars for about 7 months. What we've been doing on the way there is we've been doing trajectory correction maneuvers. Those are designed to get us targeted to exactly the right spot in the atmosphere that we need to be in order for us to land where we want to land on Mars. So we've done 4 of those so far. We have 1 more potentially to go. You'll see that we have TCM-6, so you say he can't count. We actually had an opportunity to skip one of them because our navigators did such a good job. We didn't do TCM-4. We're working right now on TCM-6. We're actually looking really good. We might even be able to skip that one because, again, the navigators have done such a great job really targeting us for where we want to be. So we're going to keep working on that for the next several days, working on the trajectory correction maneuver, working on the final parameters that we're going to need to do once we get to do entry, descent, and landing on Mars. So we'll be updating those over the next few days. So while everybody's off having turkey tomorrow, there'll be a bunch of people here at JPL working all day long, hopefully taking a little bit of a break for a turkey dinner, but largely working to make sure we land successfully on Mars. So when we get there, we have lots of ways we're going to be communicating during the entry, descent, and landing process. So far, we've been talking largely with the DSN, with the spacecraft. We'll continue that all the way until we get right up to entry. At that point, we'll drop off our cruise stage, and we'll be using our UHF antennas to talk to MRO, Mars Reconnaissance Orbiter. That's our main method of communication for knowing that EDL went successfully. But MRO does not have real-time capability to send data back to us so that we know exactly what's happening right when it's happening. So in order to have that, we brought along 2 CubeSats called Marco, which Andy's going to talk about in just a little bit. Those will be actually giving us real-time information as we go through the entry, descent, and landing process, getting through the parachute deployment, heat shield separation. Marco is going to be telling us, hopefully real-time, that that's happening. Once we land successfully, then we'll also have Odyssey, which is another orbiting asset at Mars, which will come by later and tell us that our solar arrays have successfully deployed. So really, we're using all of those assets there to make cell phone calls, essentially, to get back to Earth. So let's go to the next video, and you can kind of see what happens on our entry. You can see InSight here in the middle. The 2 Marcos that have been following us the whole time, the whole 7 months, will be tracking us as we do our entry, and you can see Mars Reconnaissance Orbiter, or MRO, kind of coming up and catching us as we go through the entry, descent, and landing process. So that is basically how we're going to do the communication. So it's going to be very exciting. We have lots of different ways to be hearing from InSight as we go through entry, descent, and landing, and then once we're on the surface. So what I'd like to do next is introduce Stu Spath, who's the project manager for InSight over the last 7 years. So Stu.
All right. Thank you. Thank you very much, Tom. Lockheed Martin is, of course, thrilled to be part of this mission. It's been a while going to the red planet, and with just 5 days to go, we are very excited. As Tom said, I've been on since the get-go with Tom 7 years ago, so I do have a lot of blood, sweat, and tears invested in this, and I'm looking forward to a nice, safe touchdown on Monday. If we could roll the first video, please. Our role at Lockheed Martin is to design, build, test, and operate the vehicle. Here you see us lowering down into the thermal vac chamber, and here's a video of us installing the heat shield, the protective thermal system that keeps us safe during the atmospheric entry. That was right before we shipped to the launch site. The image you see here now is kind of the fully dressed out version of the lander in the Denver High Bay. Let me give you a few fun facts about the lander. It stands about 3.5 feet high, or a little bit over belt high to the technicians that you see working on it right here. The length, tip to tip, from solar array end to solar array end is about 20 feet or so, which is about a 75 Lincoln Continental. And I should know, my dad drove one for 10 years. And the mass is about 830 pounds, so maybe think about a Harley Davidson, if you will. That's fully fueled. We will spend about 100 pounds of fuel getting to the surface during our descent and landing. One of the critical things after we touch down, of course, is power. So the solar arrays, as you see in this image, are a critical portion. So if we could roll the next video, I'll talk a little bit more about power and the solar arrays. This video is a time-lapse version of the actual deployment in our Denver labs. And you can see them unfurling in this shot here. This is obviously much faster than will happen. What we'll do when we touch down is wait till about landing plus 16 minutes with no solar array deployment. The reason we do that is we kick up quite a bit of dust during the landing process. So we want to give that a chance to settle out for 16 minutes, and then we'll command the deployment for about 16 minutes further from there. You see a nice close-up of the solar arrays there. It's interesting to know that that the solar arrays have 3,200 individual solar cells on them. So it is quite an effort to get those all installed, and then they furl up like a Chinese fan, if you will, tucked up under the lander. The power of the solar arrays is about 1,800 watts on Earth on a nice, clear, sunny day. But unfortunately, Mars is not Earth. So at Mars range, we're actually only about 600 watts, which instead of a hairdryer, 1,800 watts, it's more like a blender, 600 watts at Mars. And on top of that, Mars typically has a fair amount of dust in the atmosphere. So when you take that into account, we're more like about 300 watts, or a little cake mixer. So a mission like this on a cake mixer power is a big challenge. And we achieve that by sleeping a lot. About 90%, greater than 90% of the time, the spacecraft is actually asleep, and the science instruments will be on doing their business, and we'll wake up for communication passes and health and status checks. If we go to the next video. Obviously, landing is what we're all about here today, and so let me point out a couple of views of some of the key landing components. Tucked up underneath the lander here is the main component. That's the landing radar. It provides us the altitude above the surface, and any good pilot will tell you it's tough to land without knowing your altitude. So that's a pivotal part of the equation. These instruments right here are our descent thrusters. We have 12 of those. Each of them is about 68 pounds of thrust, and they pulse about 10 times per second to softly slow the descent and get us down to about 5 miles per hour at touchdown. So that's a pivotal part. And finally, the legs here, you see it's a tripod system, 3 landing legs. Think of those as shock absorbers on your car. As this touches down, those absorb the touchdown velocity, and they can actually compress up to 10 inches, which will account for slopes and terrain, et cetera. Tom briefly talked about the communications. This is the direct Earth medium gain antenna, and over here is the UHF antenna that does send the data up to Mars Reconnaissance Orbiter and Mars Odyssey. We work closely with those teams, the spacecraft team operating back in Denver, and the teams here at JPL are closely in coordination with the InSight team to make sure we get all that data back. So that's kind of a snapshot of what the lander's all about, and to hear more about the actual timeline of events on landing day, let's go to our EDL lead, Rob Grover from JPL.
Well, I have the great privilege of leading the EDL team, which is comprised of some very talented people, not only from JPL, but also from Lockheed Martin, Stu's organization, and also the NASA Langley Research Center and NASA Ames. And the team has been working for many years to make sure that the landing goes successfully on Monday. And of course, EDL means entry, descent, and landing. And that means that the team is responsible for taking the spacecraft from the top of the atmosphere all the way down to the surface. And we're going to enter the atmosphere at 12,000 miles per hour after our journey from Earth to Mars. So you can, that is a very high speed. And the whole purpose of the EDL system is to take that very high speed and down to 5 miles per hour when we get down to the surface. And that all happens in 6.5 minutes. And that's going to be kind of the main event on Monday. And I want to spend a little bit of time walking you through what to expect, what's going to happen during those 6.5 minutes from the top of the atmosphere down to the surface. So I'd like to roll the animation, please. So we will approach Mars, and the first thing we do is get rid of our cruise stage, which will be about 7 minutes before entry. We enter the atmosphere, and of course at 12,000 miles per hour, we're going to generate a lot of heat, up to 2,700 degrees Fahrenheit. When we get down to 7.5 miles or so, we'll deploy a supersonic parachute, which is about 39 feet in diameter. That'll provide a lot of the remaining braking for the system before we get to the surface. We drop the heat shield off 15 seconds after we deploy the parachutes, and then the legs spring open 10 seconds later. Our radar starts looking for the ground, and when we're about a little less than a mile above the ground, we separate from the parachute, fire up 12 descent engines, and those provide the rest of the braking and take us down to the surface. We have a constant velocity phase, which sets us up for touchdown. And you can see we will then make a soft landing at 5 miles per hour. And so there's a little bit of time where the dust will have been generated, and so we'll wait for that to settle. And we'll actually take a first image shortly after we land, and it may look like this if you go to the next image. And this is what it will likely look like a very flat place. Our landing site is Elysium Planitia, which Elysium means in Greek an afterlife paradise, although that may not look like paradise, but it is very flat, which Planitia means flat. And so it's an excellent place for a landing. As landing engineers, we really like this landing site. It's flat, it doesn't have many rocks. It's a very safe place to land. Once we've landed, once we've touched down, we're not quite done yet. In order to be completely successful, we have to deploy a set of solar arrays. And if you go to the next animation, you'll see a deployment. The solar arrays will deploy, they'll be commanded to deploy about 16 minutes after we land, and the deployment should take 16 minutes itself. So we should have the arrays out about 32 minutes after landing, and we'll get actually a confirmation of that about 4 hours after landing that we know that they're successfully out. We have a bunch of activities going on this week as we approach Mars, as you can imagine. And one of the important ones is we have a team of weather forecasters, basically a team of atmospheric scientists here at JPL, who are giving us daily weather forecasts, or kind of the expected weather at Elysium Planitia on landing day. In fact, I just came from the morning weather briefing. We have it every morning. And I want to, they actually use the MRO spacecraft to actually take temperature measurements of the Martian, of the globe, basically, and generate basically a weather map of Mars. And I want to show you that in the next animation. This is a temperature map, and the orange and kind of yellow areas in the temperature map of Mars show dust activity. So we use it to observe whether there's dust storms going on. And in this animation, this starts back in early November and shows up until a few days ago. And you can see there was a regional dust storm down around the South Pole, down at the bottom of the map, and that slowly dissipated. But over on the right, you can see the InSight landing site, and it has remained very stable, and the green means kind of background conditions. And so for the last month or so, things have looked really good. If you go to the next graphic, which is, looks like we may have skipped one there. There we go, okay. If you go to the next graphic, this is our most recent weather map. So this gives a good indication of in 5 days, I think probably, we're hoping it'll look much the same, but it's very across the whole globe, there's not much dust activity at all. So we're expecting to have a very plain day on Mars for the landing, and we're very happy about that. And in fact, we'll probably be surface temperature when we land. It'll be about 4 degrees Fahrenheit, so it's going to be nice and cold. And so it's definitely, probably don't need an umbrella, but you may need a coat, and definitely recommend a spacesuit too if you're there at the landing site. In addition to observing the weather this week, we're also paying very close attention to where we're going to land. And so if you go to the next graphic, we had just finished our last course correction maneuver last Sunday, which was TCM-5, which is the first time that we've actually been very close to our landing site. And actually, if you go to the next slide. Well, okay, so we have, up until TCM-5 on Sunday, we were about 100 miles away from our landing site, our landing ellipse. And since we've executed TCM-5, our ellipse has moved now very close to our desired landing target. Right now, or at least in our latest, or at least our navigators are telling us that we're about 4 miles away. So we're very close right now. And as Tom mentioned, we're going to continue to watch that this week. We're going to get more tracking data, and the ellipse is probably going to move around a little bit. It'll get a little smaller as we get more information about our trajectory. And we may not need our last course correction maneuver, which is scheduled for Sunday, and we'll make that decision at the end of the day on Friday. So we're very excited that our landing ellipse is now very close to the right location. So it's a great week. Things look very good for the landing. The weather's cooperating, and we're very close to our landing target. So we're looking forward very much to Monday after many years of work. So I'd like to now introduce you to Anne Marinin, who is the Marco B mission manager, and she's going to tell you more about Marco.
Hi, so Marco is a mission that launched with the InSight spacecraft, same rocket, different mission. And Marco, it's a mission of 2 small satellites that will fly by Mars on November 26th, the same day when InSight goes through its entry, descent, and landing. That was no accident. Marco is a technology demonstration mission. So the purpose of Marco is to fly 2 small satellites for the first time in deep space. It's the first time that satellites about the size of a briefcase have flown by themselves. Well, people on the Earth are actually operating them, but they're flying by themselves in deep space for the first time. They've been on orbit, in a heliocentric orbit, for about 200 days today. And right now, both spacecraft are working. The team is thrilled. And there are a lot of firsts with Marco. So Marco has to make its own way to Mars. It has to do essentially the same thing that the InSight spacecraft does on its cruise. We had to go through trajectory correction maneuvers. It has to generate its own power. We have to talk to the Deep Space Network. And talking to the Deep Space Network and doing all these trajectory correction maneuvers in deep space it's the first time that this has been demonstrated on a CubeSat platform. So the team is very excited. And if you play the animation, one of the things we hope to demonstrate now that the Marco satellites are still working is a communications relay architecture with the InSight lander. So as InSight goes through its entry, descent, and landing, it will be sending up UHF data in green, and the Marco satellites will be listening to that data and relaying it back to Earth almost real time, as was mentioned earlier. The InSight spacecraft is not dependent on Marco for its mission success. The Mars Reconnaissance Orbiter will be flying by, collecting that same data, but not relaying it until about 3 hours later. If it works, the 2 Marco spacecraft will relay the data for InSight entry, descent, and landing almost as it's happening, which would be very cool for both the Marco team and the InSight team to figure out what's going on with the lander as soon as possible. The Marco is a technology demonstration mission, so instead of having a science instrument on board, it has a whole bunch of different technologies that we're demonstrating, and I'll talk about those a little bit later, but if you put up the next image, please. We have an engineering camera on board, and the camera was put on board to verify the deployment of one of these new technologies, a reflector array antenna. And so in this image, on the right-hand side, you can see the actual antenna, the top third of that antenna, partially illuminated by the sun. On the left-hand side, you can see the antenna feed, also illuminated by the sun. And the cool thing about this picture, if you go to the next slide, there's Mars. It is the first image of Mars that was taken from a CubeSat. It was about 8 million miles away from Mars when this picture was taken. And so we're having fun with the camera. We'll see what we can do leading up to InSight EDL, but right now the team is focused on getting to EDL and supporting the InSight mission. So that's the closest thing we get to a kind of a selfie of Mars on orbit. We have a 2-scale model of Marco here. So when I say it's a small satellite, I mean it. This is the actual size. When everything is folded up, it's about the size of a briefcase. Each Marco satellite is about 30 pounds each, and the two satellites are virtually identical. And we fly 2 of them just in case one of them fails. We can have another one as backup. So this is the antenna that you saw in that image. It works a lot like the TV antennas you see on the side of a house. There's an active element here, the feed, that actually sends a signal. And then this, like the dish on the side of the house, reflects that and focuses the signal back to Earth. This antenna was specially engineered and designed to be completely flat, so it makes very efficient use of the volume and can fold up and fit very nicely on top of the spacecraft when it's all folded up for launch. The antenna that we use to listen to InSight is on the bottom here. It deploys out and is held in place by springs. This is tuned to the InSight UHF frequency, so as Marco flies over Mars, it will be listening to that data from InSight, and then the radio on board, which is another new technology that Marco is demonstrating, developed by JPL. That radio then takes that data and sends it back to Earth on a different frequency using this antenna. And the camera that took the image of these 2 objects is tucked away in the corner right there. So as I mentioned, Marco has to do pretty much everything that InSight does. There's about half of the spacecraft volume is taken up by propellant. So Marco has done its own trajectory correction maneuvers using fire extinguisher fluid. I'm not kidding. So we heat up the fluid, and it comes out as little tiny puffs, but that is enough to adjust the trajectory so that the Marco satellites fly by Mars in the exact position and time that it needs to listen to the InSight signal as it lands. So there's tiny little thrusters on this side of the spacecraft that are used to do that. We also generate our own power. It is significantly less than what InSight mentioned. So we have 42 solar cells that generates about 17 watts of power, which is a couple night lights. So not even a blender. So Marco has crammed a lot of new technologies and new capabilities into a very small volume. The team is thrilled with how it's done so far. And given how well it's done so far, we're really hoping that this becomes a pathfinder for even more small satellites to go into interplanetary space. And we're excited for Monday. So back to you, Veronica.
All right, thank you, Anne. I'd like to invite all of the speakers to come back up on stage. We're going to take questions now. We will take questions here in the auditorium. We are also taking questions from the phone line from news media. If you are on that phone line, please hit *1. That will put you into the queue for the questions. We are also taking questions over social media. So if you have a question, I believe we've been requesting them all day already on social media, but if you have a question, post that to your social media account with #AskNASA. We will answer some of those during the briefing, and we will continue to answer those during the day, even after the broadcast. I'm going to start, let me check here to see if we have one in the auditorium. If not, I will go to the phone line. We're going to start with one here in the auditorium. Go ahead and state your name and affiliation, please.
Hi there. Ian O'Neill with Scientific American and HowStuffWorks.com. This is an EDL question, I suppose for Rob. How does the EDL for InSight differ from the Phoenix EDL?
That's a very good question. How does InSight EDL differ from Phoenix EDL? And the answer is very little. It is actually, the spacecraft itself is nearly identical. There are a few differences, but the spacecraft itself is nearly identical. The difference in the landing challenge is that Phoenix was about a little more than 1.5 kilometers lower landing site elevation. So the InSight landing, we have a little bit less time to get things done. And that's probably one of the biggest things. The other is that we're landing during dust storm season, so we've had to design the system to be successful in a variety of different atmosphere conditions, although it looks like right now that we're not going to have any dust storm activity to deal with.
Thank you.
We're going to take one more here in the audience.
Hi, I'm Ryan Blackshear-Vargas from Spectrum News. Any chance that it'll land early or late?
Yeah, go ahead.
Sure, yeah. There is, if we're a little bit shallower, a little bit steeper in our entry flight path angle, and we have a little bit of tolerance there, we could land a little bit in different time. It can vary, the landing time can vary by about a minute or so, plus or minus, depending on what happens. The fact that we're kind of narrowed down and kind of know our atmosphere will make that uncertainty even less, so we're in good shape.
Okay, we're going to take one more here in the audience, and then I'll take a couple from the phone lines. If you're waiting on the phone line, please stand by. Go ahead.
Steve Gorman at Reuters. How high up will will the spacecraft be at the time that it begins entry?
Go ahead, Rob.
Sure. Yeah. We generally consider it about 77 miles above the surface, or 125 kilometers.
Okay. And the decision on the final course correction will be made Friday, even though the correction, if you do it, the TCM will be done on Sunday. Is that right?
That's right. Yeah. Yep.
Do you know what time Friday we'll know?
Well, we have our decision meeting is in the early evening on Friday, so that's when we'll make the decision.
Thanks.
All right, I'm going to take a question from the phone line, and then we'll come back here into the room. But let's go ahead with Irish TV. Go ahead with your question.
Thanks very much, Veronica. It's Leo Enright here. I'm just wondering about the call-outs post-landing. I don't recall chewing my knuckles for 4 hours to know whether Phoenix had deployed its solar arrays. So I just wonder how the call-outs, the real-time call-outs, are going to work. How soon will we know that, for instance, the deployment has happened? All of that.
Yeah, so I'll address that question. The reason that we don't have immediate information about the solar arrays is, as Stu said, we have to wait literally for the dust to settle for about 16 minutes, and then it takes another 16 minutes or so for the solar arrays to actually deploy. At that point, MRO has gone behind Mars, so we can't get any more information up to MRO from the spacecraft. And Marcos have continued on their flyby, and they're also out of range. So the next orbital asset that we can communicate with is Odyssey, Mars Odyssey, and that comes up at about 5.5 hours after we land. So it's basically orbital dynamics is why we can't get information any sooner than that. With Phoenix, it was at the pole, so it got much more frequent overflights. So that was the main difference between InSight being at the equator, Phoenix being at the pole. So I think that...
I'll just add, Tom, that the solar arrays, the spacecraft's entirely capable of taking care of itself during that period. It'll autonomously command the deployment of the solar arrays, and if for some reason it doesn't correctly deploy them, it has opportunities, 3 more opportunities on its own to recommand those actuators to deploy those. So it's not like it's going to try once and then wait for the ground. It'll be on its own, and it's been tested and ready to fly that way.
So if I may follow up, we will know that the landing has been successful. We won't have to wait 5.5 hours for that, I hope.
Yeah, that's correct. We will, especially if the Marcos are working as planned, we'll get very close to real-time information that we've landed successfully. We also have on the spacecraft an X-band beep that we'll be sending roughly about 7 minutes after we land. That'll be the spacecraft telling the Earth that everything looks good. But then we'll have to wait for that Odyssey pass to finally know that the solar arrays have been fully deployed. And there's no getting around that, just its orbital dynamics.
All right, we're going to take one more question on the phone right now. Space News, go ahead with your question.
Hi, Jeff Faust of Space News. Question for Ann. I don't know if there's any thoughts about any sort of extended mission for the Marco CubeSats after the Mars flyby?
Not right now. The team is focusing on getting 2 EDL.
Hey, Jeff, that's the answer I asked to be given. No, I'm a strong believer that focus is what creates success. And I think you should know that we've had, of course, discussions about what's possible. And we're going to have these discussions at the back end of this exciting weekend.
Okay, one more phone call, and then we're going to go here in the room to social media, and then more questions from the audience. So we have AP on the phone line. Please go ahead.
Yes, hi. Marcia Dunn here for Rob. You mentioned it will be about 4 degrees Fahrenheit at touchdown. The press kit talks about 18 degrees. I'm wondering, do you have the latest forecast? Is that what's revising the temperatures down? And if so, what are the lowest lows going to be?
Well, I'm not actually the right person to know all that information. I got that estimate from our power engineer, the 4 Fahrenheit, which was actually at the lander deck height, and so I think it varies quite a bit depending on where you are above the surface. And so I think at night it could be as cold as 180 or something like that, minus 180 Fahrenheit.
Yeah, I think actually at the surface level it's closer to like 40 degrees Fahrenheit. So there is a huge variation just in that 3 feet. But one of the things we actually will be doing is we have a temperature sensor on board the spacecraft. We didn't really talk about that at all, but we have a bunch of sensors for pressure, wind, thermal that will be, and a magnetometer that we'll be using basically over the first week, especially to characterize our landing site. So we'll be able to give you a much better idea of what the temperature is every day.
Great, thanks.
Okay, we're going to take some questions from social now. So Stephanie, do you have some good questions coming in?
Absolutely. We're having an extremely lively discussion in the YouTube chat, and the Ask NASA questions are pouring in on Twitter. Laura Reeve on Twitter has a great question for mission managers here. On behalf of her middle school students, she asks, how does communication work between different parts of the design and building teams for a project like this, and how important is that communication?
I'll let Stu answer this as well, but the communication is critical, actually, especially as I mentioned, we have international partners, we have domestic partners, where very rarely are we all co-located together, so we have to come up with all kinds of different techniques and methods of communicating what's going on every single day. As we have design progressing or any issues that we have to work, we have to get together via all kinds of interactive things online, plus we try to do as many trips as we can to actually do face-to-face communication, because there's nothing really substitutes for that. So Stu, why don't you talk a little bit about what you do on the spacecraft side?
Yeah, definitely. I'm dating myself a little bit here, but I go all the way back to the Magellan time frame, and anytime there was a big critical meeting, the entire Lockheed Martin team would fly out to JPL or vice versa, and it was much more of a face-to-face environment. We still preserve that, but with the new technologies these days, we can all be at our home institutions, including our European partners, and get a lot done. And really, it's a good team environment where we're able to share information very collaboratively, and it's really a badgeless environment where everyone's working to a common goal, so there's no turf wars or anything like that. It's a good team.
All right, and we've got a question for Dr. Z. Martian Manish on Twitter would like to know, how will InSight help potential future human space exploration to the Red Planet?
What InSight will do is really give a much better understanding of the inside of the entire planet, and with it, as we're going to learn from the science panel coming right next, with it about the history of the planet and also its entire environment and geologically and otherwise. We will learn major ingredients about the history, but also the current state of the planet, its geology, and together with the information that we have at the surface, really get a much better understanding of the entire environment that will be faced by humans. That's what we want. Before we go with humans, we want to know everything. We want to know the radiation from the top. We want to know whether there's going to be volcanic activities from the bottom. We want to understand whether there's water on the surface, below the surface. We want to know whether there's resources. So it's just part of that knowledge that's such a critical element of human exploration.
And Anne made it clear that you're very focused on the Marco team on getting to EDL, but Emily Lochtawala from the Planetary Society in our YouTube chat is asking, what does happen to the Marco CubeSats after landing day, and how long can we remain in contact with them?
That's a good question. So the Marco satellites, they don't go into orbit. There's not enough of that fire extinguisher fluid on board to do that. So they will just fly by Mars, and they'll end up kind of in an orbit between Earth and Mars. And it will start getting farther and farther away, and I don't have a good timeline of how long we could actually get that signal, but eventually it will be too weak for us to actually be able to hear from it anymore.
Okay, we're going to take it back into the rest of the audience. We'll come back to social in just a couple minutes, and I understand we have a question here from ABC. Go ahead.
Hi, Stephen Coleman, KABC, Channel 7. What happens if one of the arrays, or both of them, fail to deploy? Can you continue the mission without them?
Yeah, so if we definitely need to have at least one of the solar arrays deployed because we are 100% solar powered. Our battery is not going to last more than about 1 Mars day without the solar arrays fully deployed. If we get partial deployment, we will have to look and see exactly how much energy we are generating. Stu mentioned in his discussion that we have a little bit of variation in how much power we might see over the different points in time, so we're just going to have to take an engineering assessment and see what kind of emission we still have. But clearly, Lockheed Martin's done an excellent job of making sure that we are going to get those solar arrays deployed. So I have full confidence that that's going to happen, and hopefully we don't have to worry about any of the contingencies. I don't know, Stu, if you want to add anything?
No, that was well summarized. We've done a lot of testing during the first ATLO period, and then a bunch of retesting during the second integration and test period. So we're highly confident they're in good shape, and they're good to go.
Okay, we're going back to the phone line. Leo Enright has a follow-up question. Go ahead, Leo.
Thanks very much, Veronica. I hope this isn't too much detail, but in the video, we saw Marco doing real-time relay and MRO rising, but there seemed to be 3 MROs. Now, unless I've been asleep, there's only one. The 2 that I saw were middle and south. So I was a bit puzzled as to how come there's 3 MROs, or was there something I completely missed?
No, you did see 3 MROs. What that's representing is sort of the different times in which MRO might actually be visible depending on exactly when we're entering the atmosphere. So it's basically sort of a best case and middle case and worst case in terms of the coverage that we're going to get from MRO. So there really is only one MRO. It's sort of in that range of areas where it probably will be when we do our entry, descent, and landing.
Okay, any other questions in the room? If we don't have any other questions from media here in the room, go ahead. We'll take yours, and then we'll go back to social. Go ahead.
Did you say it'd be 4 hours or 5.5 hours, or is that a range for how long it would take?
I believe you're talking about when we're going to get information from Odyssey. It's going to be about 5.5 hours after touchdown.
Okay.
Okay, we have time for one more social question. Stephanie, go ahead.
All right. So Phil Moyer over on Twitter says, with InSight's design service life and given the record of your Mars probes far exceeding their expected lifetimes, how long do you think InSight will live?
Well, we have not designed any life-limiting features into InSight, so it's a function of how long we're going to continue to collect solar power and be able to run the mission that we want to run. We're designed to last 1 Mars year, so that's 26 Earth months. And so we think that with the accumulation of dust on the solar arrays that will make it at least 1 Mars year and get back to science that you're going to hear about in just a little bit. But we'll have to evaluate where we are after that year and how much science we've got back and make a case for continuing if we're making truly groundbreaking science that we expect to be getting.
Okay, we're going to wrap it up at this time with this panel describing the spacecraft. We are going to be back at the top of the hour at 11 a.m. Pacific time, 2 p.m. Eastern time to discuss the science of the mission and the science instruments. So there's a lot of really cool stuff on this spacecraft. Please come back. Also want to promote for you that the next news briefing following today will be on Sunday, just 1 day before landing, and we'll get a final update on the status of the spacecraft at that time. And then landing landing day again. It's Monday, November 26th. Our commentary will begin at 11 a.m. Pacific time, 2 p.m. Eastern time, with landing taking place about an hour later. And again, there's multiple websites where you can watch the landing live. You can go to nasa.gov/live if that's the easiest one for you to remember. On our toolkit page at go.nasa.gov/InSight toolkit, you'll see two tabs there. One is how to watch online. It has a chart with numerous platforms where you can watch on YouTube, on Twitter, on Facebook. Again, our 360-degree broadcast will be on our YouTube channel. There's also how to watch the landing in person. There are numerous events taking place across the country. You can check from California to New York to Times Square in New York. You can even be standing there in Times Square and see our landing commentary on the NASDAQ tower. There's even some viewing parties in Europe. So those are all marked, again, at that toolkit page. Just click on Watch in Person. We will resume at 11 a.m. So in the meantime, we're going to replay some of the videos for this particular mission, starting with a description again of entry, descent, and landing, and the nerve-wracking white-knuckle 6.5 minutes to get to the surface of Mars. So that'll wrap for now, and we'll be back in about 15 minutes. Thank you for joining us. Welcome back. We're at NASA's Jet Propulsion Laboratory in Pasadena, California, and we're here to talk about the InSight mission. The InSight mission has a date with Mars come Monday, November 26th. It will be landing on the red planet. That landing takes place at about noon Pacific time, 3 p.m. Eastern, with commentary broadcast live about an hour before that. We're going to talk to the science team now, the science panel, and they are going to explain to us how the InSight mission will be detecting the vital signs of the planet. We have instruments that we'll be placing on the surface of Mars to tell us more about how Mars formed and, in fact, how all rocky planets formed. I'm going to begin by introducing Dr. Lori Glaze. She is the acting director of NASA's Planetary Sciences Division.
Great. Thanks, Veronica. I'm excited. I know you are too. I was already excited when I got here. And then sitting through the mission briefing this morning, I'm even more excited than I was before. How exciting. 5 more days and we'll be there. We'll be landing yet another planetary mission on the surface of Mars. Each of the planetary missions, each of NASA's planetary missions, is on a quest to answer important questions about how our solar system formed and how it changed over time after it formed. We've sent lots of different missions to different worlds and different corners of the solar system, and they're each trying to answer that same question in different ways, different types of observations at different types of worlds. Some of the most fundamental questions that we have about how our solar system formed and how it evolved have to do with how did the rocky planets in our solar system form and evolve. The rocky planets, Mercury, Venus, Earth, Mars, and even our moon. Each of them are similar. They're rocky planets. Some of them have atmospheres, and they have structures that are similar, have similarities and differences. If I could have the first graphic, this graphic actually shows a cutaway of Earth and Mars and the moon. And what you can see inside of each of these rocky planets is that they have at their center a core. And that core can be solid or it can be molten. And then outside of that core, there's a middle section that we call the mantle, which makes up the bulk, most of the mass of each of the rocky planets. And each of those rocky planets is covered with a thin crust. What we really want to know is what are the similarities? How are they different? How are they the same? What are the relative sizes of those different parts of the interiors of those rocky planets? The different sizes. Is the core, is it molten or is it solid? Is that the same for each of the planets? That we need to know. Most of the missions we've already sent to Mars are either making observations from orbit, getting at the surface conditions, trying to understand what's happening within the atmosphere on the surface, sending landers and rovers, again, just scratching at the surface to understand that surface environment. If we want to understand what the insides of these rocky planets are like, we have to make different kinds of observations that can really penetrate down into the center of the planets. The types of measurements we make on Earth are things like seismic measurements, understanding the level of seismic activity, thermal measurements, heat flow, understanding the amount of heat that's getting out and released from the planet. We do this on Earth on a regular basis. We've actually even done these types of measurements on the moon. With the Apollo program, we had astronauts that brought these types of experiments and deployed them on the surface of the moon. But if we want to make these kind of measurements at Mars, we haven't sent astronauts to Mars yet. They will be going at some point in the future, and a lot of what we're doing is in preparation for that. But if we want to do this on Mars today, we have to do it robotically. And so with that, I'm going to introduce Dr. Bruce Bannert, the PI for the InSight mission, to tell us a lot about the science. And when I go off the stage, I just want to say, go InSight. Yeah.
Okay, so InSight is going to Mars to study the deep interior of Mars in order to understand how all the planets formed. I mean, we know a little bit about how planets form. They accrete from a solar nebula. As they accrete, they get hotter and hotter, both from the energy of the impacts and from radioactive decay. And then they melt and transform from sort of a uniform ball of meteoritic material into the diverse planets that we see today. Some of those planets are a little bit harsh. Venus is hot enough to melt lead. Mercury has a sun-baked surface. Mars is pretty cold today, but Earth is a nice place to take a vacation. So we really like to know why one planet goes one way and another planet goes another way. And those answers are in the details of the structure that's formed very early in the planet's history. On Mars, that structure's been preserved for over the last 4.5 billion years, whereas on the Earth, where we actually can study it pretty easily, that structure's all been sort of scrambled up, both by plate tectonics, by mantle convection, and so the evidence of the very earliest processes has been wiped away on the Earth. We want to go to Mars to do that, to study those processes, to look at how those processes came about very early in the planet's history. The main way that we're going to do that is with seismology. And the way we use seismology, when you want to study something, the first thing you want to do is look at it. And the way you look at it is you bounce light off of it, it goes into your eyes, and your brain can interpret it as an image and see a 3D image of what you're looking at. If you're looking at the center of a planet, light doesn't help you very much because it doesn't go very far through rock. So what we do is we use seismic waves, vibrations that are created by earthquakes on the Earth, Marsquakes on Mars, also meteorite strikes. Anything that starts a planet vibrating sends those waves through the planet. If I can have the first animation. This shows a seismic event on a planet, and it's showing the waves that travel through the planet, the blue P waves, the red S waves, and these waves travel through the planet the same way light would travel through a lens or something like that. And so a Marsquake is sort of like a flash bulb that goes off and illuminates the inside of a planet, and our seismometer is the eye that we use to see what's inside the planet. And by looking at those seismograms that you've seen on television, those wiggles on a graph, scientists have learned how to interpret the shape of those waves, the time which they come in order to understand the medium through which those waves travel. We can figure out what the inside of the planet's made out of. We can figure out where the different boundaries are between the rocky mantle, the iron core, and so forth. And so a seismometer allows us to look deep into the planet and understand the detailed structure. We also have a few other instruments, a few other investigations on this mission. One is a radio tracking experiment. We actually track the planet very precisely. And in particular, we're tracking the North Pole of the planet and watching it wobble as the planet rotates. And the wobble at North Pole is tied to the interaction between the planet and its core. And by looking at the wobble, its size, its frequency, how fast it's wobbling, we can actually determine the size of the core and what it's made out of. And that's very critical in terms of understanding the history of the planet and the way the planet is operating today. And finally, we have a heat flow probe. It's a very interesting device. Tilman Schmann's going to tell us a little bit more about it later. It penetrates down into below the surface, about 10 to 15 feet below the surface, and measures the temperature as you go down, and we're able to use that to extrapolate to the center of the planet and understand how hot it is in the middle of the planet and how much heat is coming out of the planet. And that heat is what actually drives the geology at the surface. And in particular, it drives tectonics, which is the quake motion of the planet, and it drives volcanism. And here to talk a little bit more about these geological processes and how InSight's going to illuminate that is my deputy PI, Susan Makar from JPL.
All right, thanks, Bruce. All right, well, every geologist and geophysicist that I know likes to climb mountains. And if we could have the first graphic. Most of us aren't lucky enough to be able to climb Mount Everest. However, some of us are privileged to be able to study the mountains on Mars. And as you can see, the mountains on Mars actually dwarf Mount Everest. These volcanoes are not only the tallest mountains, but they're the tallest volcanoes in our solar system. These volcanoes actually formed billions of years ago on Mars. And when they formed on Mars, they actually covered about a quarter of the planet. You can see Olympus right here, and you can see this whole volcanic region that formed early in the history of Mars. And if we go to the next graphic, we can talk about how these volcanoes formed. For me, really the most compelling thing about volcanoes is the fact that they are really conduits from material way deep in the planet to the surface. Not only do volcanoes spew lava on the surface, they also release gases into the atmosphere. They release things like water vapor, carbon dioxide, methane, all the things that we need to actually form an atmosphere. So the best analogy between the volcanoes on Mars and those we have on Earth are actually places like Hawaii. So Hawaii is an example of a hotspot volcano. So material from deep in the mantle, actually at the core mantle boundary, rises up in a plume over tens of millions of years. And as they come up and intersect with the crust, it forms volcanism at the surface. Now, on Earth, we have plate tectonics. So when that plume comes up and hits the surface, it actually is intersecting a conveyor belt. The plates are moving slowly, slowly across that plume. And so one volcano forms, and it's carried off downstream. So actually at Hawaii, we see those few volcanoes at the surface now above the ocean. But it really is just one of a series of volcanoes, dozens and dozens of volcanoes that are now under the surface of the ocean. On Mars, we don't have plate tectonics. So when that plume comes up and hits the crust, it stays there in one place. And so instead of making a line of volcanoes, we have a series of volcanoes. And you can see this complex of volcanoes that was formed above a mantle plume early in Mars's history. The thing that we're really looking forward to for InSight is being able to go back in time. Mars formed these volcanoes in its first couple billions of years at a time when there was a magnetic field, when there was liquid water on the surface, all conditions that we think are important for the habitability of a planet. For InSight, we're going to learn about the interior structure, the core, the crust, the mantle, the heat sources in the interior. And with that information, we'll be able to better understand how the interior of the planet affects the surface environment on rocky bodies, not only on Mars, but in our solar system and on other rocky bodies around other stars. I personally have been waiting for this information for decades, and I'm super excited to start getting this lander on the ground and start taking this data. Up next to tell you about some of the instruments that will acquire this data for us is Philippe Laudet, and he'll be telling us about the SIZE instrument. All right.
Okay. Good morning. My name is Philippe Laudet. I'm working for the French Space Agency, which is called CNES, so sorry for my French accent. And I have been the project manager of the SIZE instrument for now more than 7 years since the pre-selection of the Discovery program in 2011. So as you have understood, InSight will make measurements of quakes and meteorite strikes on the surface of Mars. For that, he will use a seismometer SIZE, which is provided by the French Space Agency, CNES, and also by IPGP, who is a French laboratory for geophysics research, and it's our French PI for SIZE, Mr. Philippe Laudet. And as you can see, I don't know where the film is. Oh, sorry, I didn't see the screen, thank you. So this instrument will be deployed exactly on the surface of Mars in order to have better accurate measurements of the seismic waves. And the major engineering challenge we had due to that position on the surface is to protect the instrument from thermal variations and also from the wind of Mars, which is very aggressive for that kind of instruments. So you have a protection on the seismometer itself, and another one is the wind and thermal shield, which is being deployed on the film, which is deployed in the second time by the same robotic arm, exactly on the seismometer. And there is absolutely no mechanical contact between both, because the windshield will move with the wind, but not the seismometer, of course. Okay, and as you know also, we are not the only instrument on the surface. We have another one, which is a German one, HP Cube. And I leave the floor to Tilman Spohn, who is going to talk about HP Cube. And I tell you goodbye, thank you, and see you on Mars next week. Bye-bye.
Hi, greetings from Germany. I'm Tilman Spohn from the German Aerospace Center, DLR, and I'm the lead of the heat flow probe, the HP-cubed experiment. DLR has been building this instrument and contributed that to the mission. Now, as Bruce already told you, we're taking a set of temperature sensors down to a depth of 10 to 15 feet to measure the temperature and the heat that is coming from the interior towards the surface. Now, how are we going down? Let's play my first animation. Can we have the first animation, please? Okay, here is the winding mechanism in the mole. We nicknamed that penetrator a mole that compresses the spring. And when the spring is released, it hammers, towards the tip of the mole and then propels it down into the ground. Now we stop the penetration at about 2 feet and take a measurement of the thermal conductivity. And then we continue that. Let's continue the animation. Can you continue, please? And we take we heat the mole and measure the thermal conductivity, and then we continue the penetration and take another measurement of the thermal conductivity and another measurement until we get to the target depth of 15 feet. When we're down there, we will then we'll then activate the temperature sensors, 15 temperature sensors that measure the temperature profile down to a depth of 15 feet. And by combining the temperature increase with the thermal conductivity, we can actually calculate the heat flow. Now, I'm very excited to come here on Friday and then attend the landing event. And then, of course, the experiment, the penetration first, and then the measurement of the temperature and the thermal conductivity and the heat flow, because that will help us decipher, the energetics or the activity of the planet. And this is something that geophysicists have been looking forward, for a very long time. And with that, I'd like to hand back to Veronica to continue the presentation. Thank you very much for your attention.
All right, thank you so much, and stay where you are, Tilman. We're going to bring the rest of the panel back up on stage now to do some questions and answers. A reminder that we will take questions here in the room. We have some media on the phone line. If you're on the phone line, please hit *1. That will put you into the queue for a question. We're also taking questions on social media. Just use #AskNASA and send those in to us. We'll take some during the broadcast. We'll continue to answer those even after we go off the air today. So we're going to open it up here first in the auditorium, and then we'll go probably to phone lines next. So go ahead. Thank you.
Hi, Ryan Blackshear-Vargas again from Spectrum News. You mentioned there's lots of questions that will be answered. What's the #1 question you want answered after 2 years?
I think the #1 question we want to answer is what's the structure and the energetics of the interior of Mars. And so we have several things that we want to measure. We want to measure the thickness of the crust, the size of the core, the density of the core, and the seismic velocity of the mantle, which tells us sort of what the structure of the mantle is. And those are kind of our key questions, as well as the amount of heat coming out of the planet. So when we proposed this mission 8 years ago, we put together what we call our level 1 science requirements. And these are the things that sort of we promised NASA that if you choose our mission, these are the things that we're going to measure. And that's kind of our list of measurements. And then we also are going to measure how often Marsquakes occur and how often meteorites strike Mars, which is kind of a bonus.
And then a follow-up question, how does all of this help us understand life here on Earth? Will we understand better earthquakes? Will we understand volcanoes better? Will we understand, what kind of everyday parts of our life here will the InSight mission help us understand?
Well, what it really helps us understand is how we got to where we are today. How we got to an Earth that has an atmosphere which is breathable, an environment which is in a temperature range which is comfortable for life, how we have a planet that's covered with water. These are all things that are related to the activity and the structure of the inside of our planet. It's not really, it's not obvious to everybody, but the fact that we have an atmosphere is because we've had all these gases that have come out of the inside of the planet. The reason we have ocean is because the water has come out from volcanic activity over the billions of years. And so that activity is tied to the initial conditions of the planet. And so we'd like to understand how that happened, how we got to where we are today.
Thank you. Yeah, and if I could just add to that, life started on Earth, we think, very early on in the first half billion years, and that crust is almost gone on the surface from the surface of the Earth. Whereas on Mars, that very early crust is still preserved. Those environments that it formed super early in the formation of planets, of our solar system, and so we can kind of go back in time and study those environments on the surface of Mars and understand how the conditions inside the planet created those environments.
Thank you.
Okay, we're going to take one more here in the auditorium, and then I'm going to go to the phone lines, and then we'll be coming back.
Hi, Ian O'Neill for Scientific American and HowStuffWorks.com. Going back even further than that question, how does your assembly of instruments and experiments help explain the origins of planets themselves? I mean, was it, it's almost like a time probe looking back over 4 billion years ago, but how do you hope this will add pieces to that puzzle?
Well, as you said, the structure of the planet is really formed in the first few tens of millions of years after the planet accretes. So we're not going to have much to say about how the planet actually accreted, but once it gets formed from the solar nebula, how it changes from sort of a uniform ball of meteoritic material, which is all kind of the same stuff, into a planet which is differentiated, which has a crust of relatively light rocks, and a very dense core, and a very complex system of transferring the heat from the center of the planet to the surface. These things are all kind of set up very early in the planet's history. And for the Earth, we don't really have any evidence of that system left anymore. What we have is a very evolved system. And so we want to go to Mars to see what that system looked like very early in the process. And so to better understand the physics and the chemistry of how you go from the very initial set of conditions with this sort of solar dust and ice that's accreted into the very complex planets that we see today.
And just one follow-up. In regards to meteorite impacts, how many meteorite impacts do you expect to detect with your instrumentation? And yeah, that's the question.
Well, one of the things that we want to actually find out is actually measure how many. We're sort of expecting something of the order of maybe a half a dozen to a couple of dozen in the 2 years that we're on Mars.
Cool. Thank you so much.
Sure.
Okay, we're going to the phone lines next. We've got about 3 different callers right now. We're going to start with the AP. Go ahead.
Yes, hi. This is Marcia Dunn, AP. I have a question I'd like both Philippe and Tillman to answer. NASA has a long and rich history of exploring Mars, and as the relative newcomers to this, I'd like to know from both of you what you find so captivating and magical about Mars versus other planets.
I didn't catch everything. Could you repeat to me?
She wants to know what you find fascinating and captivating about us going to Mars and studying Mars.
Everything is captivating first. It's a dream first, and after there is a big challenge because that instrument was supposed to be so sensitive that at the beginning it was just impossible to build. Okay, but we did it with the help of our partners, and particularly JPL. Thanks for that.
Would Tillman like to also weigh in?
Okay, to me, Mars is a planet that is, on the one hand, very different from the Earth. On the other hand, it's quite similar. It's half the size of the Earth, but its environment on the surface is more Earth-like than, for instance, the atmosphere and the environment of Venus. And understanding the difference between the Earth and Mars, will help us understand the evolution of terrestrial planets in general, and in particular the Earth. And this is what makes the motivation for going to Mars. And in addition to that, it's easier to explore Mars, than Venus. And therefore Mars is the first target, to do a geophysical observatory like we now do on Mars. So it's timely, and it's very much, justified to do that now.
Okay, our next question on the phone line is from AFP. Go ahead, please.
Hi, this is Ivan Kron of Agence France Presse. You mentioned Marsquakes and meteorite strikes. Can you talk in details about the other possible sources of vibrations that you might listen to?
Sure. So those are the two primary sources of vibrations that we hope to see. We also actually will probably see vibrations due to the interaction of the atmosphere with the surface. So when you have weather on Mars, you have turbulence, that actually is pushing the surface up and down. That will create, on one hand, it creates noise that makes it harder to see the Marsquakes, but on the other hand, when you start beating on a planet like that, it'll actually start resonating at certain frequencies, and those resonances are affected by the structure of the planet, and so we may actually be able to get some information from that. And finally, what we should also be able to measure is actually this is not exactly a vibration, but it's the motion of the surface up and down due to the tidal pull of the Martian moon Phobos. And every time Phobos goes overhead, it actually pulls the surface up a little bit, and then it goes back down after Phobos leaves. And so we can actually measure that. It goes about a centimeter and a half, a little over half an inch up and down when Phobos goes over. And it turns out that we can actually use that measurement as well to look at the inside of the planet, because how much that goes up and down depends on sort of the elasticity of the planet and whether the core is solid or liquid. And so we'll be able to use that measurement as it happens every 7 hours or so on Mars to probe the inside of the planet.
And if I may, could there be some magma movement at all from the inside?
There could be magma motion on Mars. The area that we're landing in is pretty featureless. I mean, it was a lava plain, but it was put down, several billion years ago. So we're not expecting any active volcanic activity in our region. It's possible that it could be happening somewhere else on Mars. It's conceivable that we could pick that up with our seismic instruments, but we're not expecting it.
Yeah, but we are in a good place. It was about 1,000 kilometers to an area that may have been volcanically active in the last 10 million years. So for Mars, that's yesterday. So we can hope that we might hear some magma deep under the ground, not at the surface, but deep underground.
Yeah.
Thank you.
Okay, we're taking one more from the phone line, and then we'll come back into the room. We're going now to space.com. Go ahead.
Thanks for taking my question. This is Megan Bartels from space.com. I had a question for Lori. I was hoping you could talk sort of big picture. Why is it that we're so fascinated with Mars and we keep returning with science missions? What is it that really captures us about the planet?
It's a great question, and Mars is an incredible natural laboratory right next door to Earth. And as I was kind of alluding to at the beginning, we really want to understand how we came up with this diversity of rocky planets in our solar system. They're all very different. Each one of them is unique in its own way, and trying to understand how they ended up so differently is a really important question. And Mars is a great natural laboratory. It's right there. It's reasonably easy to get to. We demonstrated that we can land successfully on the surface. We can conduct scientific experiments for long durations on the surface. So it's very amenable to trying to do these types of investigations. And then in addition to that, Mars has another piece of intrigue for us in that it could have potentially had a significant amount of water there in the past. We see lots of evidence of that in the geology. And so we do believe that there was a lot of water there, and it could have potentially been a place where life could have formed very early in Mars's history. And of course, trying to understand how life is or was distributed across our solar system is one of the major questions that we have. Are we alone? Were we alone sometime in the past? And so Mars is really an intriguing destination for that purpose as well, trying to really understand what those conditions were like back 4 billion years ago. Did life actually begin on Mars in that time frame? And if it did, is there any preservation of that left on the surface? Of course, that's not the focus of the InSight mission, but it is the focus of a lot of the other investigations that we're interested in at Mars. And so trying to better understand Mars in that context is important. And then finally, as was alluded to this morning in the mission briefing by Dr. Zabukin, we'd like to eventually get humans back to Mars. We're interested in a campaign now in returning humans to the moon and eventually getting humans to Mars. Again, another destination in our solar system where we feel it is amenable to human exploration and a place where we could go at some point in the future. And science drives our understanding that allows us to get humans to a place like Mars. And so the more exploration we have, the better we understand that environment, the better prepared we'll be to send humans to Mars in the future.
Great. Thanks so much.
Okay, we're going to bring it back into the room here for questions from media, and then from social media, I see our team over here working furiously collecting your questions, so stand by for that. Go ahead with your question.
Hey, Charlie Shelton with CV Weekly. I have a question about the Olympus Mons formation. What is it that is different between Earth and Mars about tectonic motion? Why do the plates not move and allow something so big to build up?
Yeah, so I mean, that's part of what we hope to learn from this mission. In fact, for the first order answer is that Mars is a lot smaller than the Earth, and so it doesn't have the same amount of radiogenic material, the same amount of heat that it starts out. So just being a smaller planet, it loses its heat more rapidly. So you need to have a vigorous convection, a lot of energy inside the planet to drive that motion of plate tectonics. People have proposed in the past that maybe very early in Mars's history it had plate tectonics. Now, we don't have any direct evidence of that, and we don't expect to see evidence of that on Mars with our mission, but it's always the things that we don't expect that turn out to be the most intriguing. So who knows what we'll find in the interior.
Follow up to that, is there any way to tell either from aerial view or a mission like this, maybe in a different area, if there is a previously active subduction zone or any of those other things, or can you tell even where any of the transform faults are? People had proposed that there might have been subduction and transform. We do see evidence for transform faults from the high resolution topography data that we have. And in the past, people had proposed that there might be subduction zones on Mars. We think that that's not the leading hypothesis for how the northern plains formed. It was previously proposed as an option for how that low topography in the northern hemisphere formed. We now think it's likely due to the presence of a huge impact early in Mars's history. And we've come to that hypothesis based on the topography, the gravity data, the geology and the faults that we see at the surface. InSight will actually be adding to our knowledge of how these two hemispheres formed. We'll be understanding the thickness of the crust, which we don't know very well at all now. We'll see perhaps if there's a difference in the composition and the thickness. We know there's a thickness difference between the north and south, but getting the exact difference between those two will help us better interpret these hypotheses. And we assume it's going to support the impact theory, but again, we'll find out. Thank you.
All right, we're taking a question right here. Go ahead.
Hello. Steve Gorman from Reuters. So two questions. One, how long, if after the InSight lands, if it arrives safely and settles safely, will it begin to conduct, will the seismometer and the heat probe begin to do its things? And then also a very specific question about the sensitivity of the seismometer. I believe you said in the past, Dr. Brenner, that it would measure seismic waves as small as the diameter or half the diameter or half the radius of a hydrogen atom. Could you give me that one more time?
Yeah, that's right. I mean, the sensitivity of the seismometer is in acceleration units, our requirement is 10 to the minus 9 meters per second squared. And if you turn that into displacement, that comes down to less than 10 to the minus 10, which if you, depending on exactly how you define it, it's about half the radius of a hydrogen atom. And that's
radius.
Yes, and we're actually a little bit better than that over part of the frequency band. Thank you very much, Philippe. We're about a factor of 5 better than that in some parts of the frequency. So yes, we're pretty doggone sensitive. And so one of the issues that gives us is that makes us sensitive to everything else that's happening in our environment. You know, if there's a little bit of wind, if the temperature changes a little bit, even if a little pressure front goes by, it's going to change the seismometer around. And so that's why we have a weather station on board, which we haven't talked about much today because it's not part of our core mission, but we have a very competent weather station. It's going to give us temperature, wind, and barometric pressure 24 and a half hours a day, every day on Mars. And so in addition to doing all this science about the deep interior of Mars, we're actually going to be contributing a lot to understanding the environment, the surface environment of Mars as well. And okay, so in terms of how long it's going to take to get the instruments going, so InSight's kind of a laid-back, slow-motion mission compared to a lot of things that we've done before. We have a 2-year mission to do our science, and so to get that mission started, we have to get our instruments on the ground. It's going to take us about probably 2 or 3 months at least to get our instruments down, and that's because we have to do a survey of the area in front of the spacecraft, make sure that we don't put the instruments down on a rock or in a hole or something like that, and then we're very careful about how we put the instruments down. You saw the animation that they had the robotic arm going and picking up the instruments and putting them down. It actually goes a lot more slowly than that, and we have a whole set of activities that we go through to ensure that when we put those instruments on the ground, they're going to be in a place where they can operate properly and get these kinds of measurements. So it's going to take us, probably a month or two to get the seismometer down, and another month or so to get the heat flow probe down and penetrating down into the surface. So whereas we're going to get some photos and some preliminary data back before that, in order to really get operating, we're probably looking at early next spring when we're really going to start bringing back that kind of science from Mars.
Thank you.
Okay, we're going to turn it over to the social media team to tell us some of the questions that have been sent in.
Well, Bruce anticipated one of the hottest questions out there that everyone was asking us, how long until we get the data? And you mentioned the cameras. Desvain on Twitter asked, does InSight take pictures? And if so, will we be able to see them?
It does take pictures, and you will definitely be able to see them. We have 2 cameras on board. We have one's called our instrument context camera, and that's going to take a picture just a few minutes after landing. And it's bolted to the bottom of our deck, and it has a fisheye view, so it's going to show about 120 degrees, 130 degrees of view just right in front of the lander, perhaps even up a little bit above the horizon, down to very close down to the spacecraft. And that shows the entire area that we're going to be trying to map out to deploy our instruments on. Then we also have another camera. It's actually attached to the robotic arm. It's a higher resolution camera, and we use the arm itself to point that camera, and we're going to be able to put together mosaics of both the area in front of the spacecraft and the entire region around the spacecraft. And those images are going to go out onto the internet more or less right away as soon as we get them. So we'll have raw images out on the internet for people to look at as the mission progresses.
Fantastic. Okay, so Winter in our YouTube chat wants to know, how will the InSight seismometer be able to map the internal structure of Mars in 3D with just one sensor? How is that accomplished? And Rabbi Cooper over on Twitter follows up, don't we need 2 or 3 to determine the inner composition?
You would think, wouldn't you? Usually if anybody knows anything about seismology, you know that you need at least 3 seismometers to do seismology. And that's true unless you get really clever about it. So we had to get clever. I mean, we actually had lots of concepts of missions that had 3 landers, 4 landers. We even had a concept with 18 landers on Mars at one time. And None of those actually ever got funded because they're very expensive. And so we had to go back to the drawing board and figure out, well, how can you do seismology, real quantitative seismology with a single seismometer? And it turns out there are quite a few techniques that are available to us. I mean, and people have used this on the Earth, but they get sort of eclipsed by the sort of array seismology that we normally do. And one of the things we do on Mars is we use the fact that Mars is small to our advantage. And what happens is that in addition to the P waves and the S waves that you normally hear about in seismology, there's also something called a surface wave, and that's a separate kind of wave that travels along the surface of the planet. And so, in addition to the P and the S wave, we actually get the surface wave, which travels to the seismometer, and there's another one that goes the other way around the planet and comes in the long way. And so there's two extra what we call arrivals. And then finally, the one that's gone all the way around the planet can go around again and hit our seismometer. And these things can keep going around. They get a little bit smaller and smaller each time, obviously. So we use that extra information to be able to figure out how far away the Mars quake is. And we can actually use what's called polarization analysis to figure out which direction it's coming from. And so instead of having to triangulate on it using multiple seismometers, we're actually able to use sort of the extra information that's contained sort of later on in the seismogram in order to get the distance and the direction. And it gets more complicated than that, but that's sort of the basic method.
We've got a mountain of questions, Veronica. How much time do we have?
I think we're good. Go one more, and then I'll do a final look in the room here to see if there's other questions. Go ahead.
Okay, well, two-parter. Okay, Oscar wants to know, is there an opportunity for citizen science to participate with this mission?
Well, we will be putting the seismic data out on the internet within a few months after acquisition. If you're a citizen seismologist, you can certainly work on it. We'll also be putting the images out, and there's a very vigorous community of photo interpreters out there that have been doing photo interpretation on Mars images for many, many years, and our images will be available for that as well. We also have something called seismometers in the schools, and we're actually going to be sending the seismic data out to schools which are participating in our program at the same time, basically, that our scientists on our team are going to get it. And so the students at various middle schools and high schools are going to be getting our data in close to real time, and they'll be able to try their own interpretations on it and so forth. And we're hoping that they don't beat us to the punch in any of the big discoveries, but we'll see what happens.
And additionally, we have a Mars Weather Service. So you can get information about the weather daily at our site. You can get wind, atmospheric temperature, surface temperature. So you'll also get a daily weather report from our site.
Okay, let me ask one more time out here in the audience. Yes, we do have a question here. We'll get you a microphone.
Scott Sullivan from the Weather Network. I'm really interested in knowing about the weather on Mars. So this, as far as I understand, is the very first continuous weather monitor that we put on Mars. Previous missions have had weather, but it's very distinct measurements every day. This is going to be, as you said, 24 and a half hours every day. Do you anticipate learning anything really new about Mars weather that we didn't know about before?
The short answer is yes. I don't know what it is. We'll have to discover it. But yes, I mean, every time we go to a planet and look at something differently with a different set of instruments in a different way, we always discover something new. And this is, as you said, this is going to be a unique data set of continuous measurements, temperature, barometric pressure, wind, speed and direction, all day long, all night, over an entire Mars season. And that's obviously going to, I think, just have an enormous wealth of scientific information for us.
Okay, we're going to take one more social media question, and a reminder that if you have sent in a question with hashtag AskNASA, we'll continue to answer those after we go off the air. Go ahead, Stephanie.
All right, so this is for all of our scientists here today. Anna M. on YouTube would like to know, what would be more exciting for you? A result that meets your expectations or something completely unexpected?
That's an easy one. Unexpected is always a lot more fun. Yeah.
I would agree with
Yeah. Meeting your expectations is, gives you a nice warm feeling, and then you say, well, what's next? What am I going to do next? If you see something that's unexpected, that always opens up a whole new doorway into something that you never thought of before, and that's what a scientist lives for, really.
Exactly.
Yeah, that's the coolest part. What we don't know now is what is the coolest part.
I was just going to say, that's what we do as explorers, right? That's why we're here. That's why we're doing what we do, is to find those unexpected treasures that are out there, the new discoveries that are going to drive the next mission and send us to the next destination.
Oh, yeah. The root motivation is exactly what they said. I have nothing to add, except perhaps one point to precise that there is a technological thing, there is the challenge of the science discovery that we are going to make. And also there was a very interesting thing during all the development, and also the following, is to work together with different culture, different languages, different money. And it's definitely very interesting that people on Earth are able to work together before we wanted to talk with Martians, for example.
Okay, that concludes our briefing for today. Thank you all so much for spending time here. Thank you, gentlemen, for joining us all the way from Germany. We look forward to having you out here for landing.
I'll be coming on Friday.
Okay. Now, I want to remind you about all the different activities we've got going on up through landing. So to watch our schedule on Sunday, which will be our final mission news conference before landing, and then also that afternoon we have a NASA social program that will also be televised on NASA TV. So we have the news briefing at 10 a.m. Pacific time, 1 p.m. Eastern time, followed by the NASA social event, which again is a great Q&A, another opportunity like this to send in more questions. That will be at 1 p.m. Pacific time, 4 p.m. Eastern time. And then landing day itself, Monday, November 26th, we want you to join us. The landing itself takes place about noon Pacific time, 3 p.m. Eastern. Our commentary begins 1 hour prior to that. And there are multiple ways that you can watch. The easiest way is nasa.gov/live. Bookmark that now so you have it for Monday. You're going to be online Monday anyways for Cyber Monday. You're going to be shopping. Just have that extra screen open. We also have a very good toolkit with a lot of in-depth information about the mission, a lot of fact sheets, and a very good list of multiple ways you can watch. That URL is go.nasa.gov/InSight Toolkit. There's great tabs there. You want to click on Watch Online. You will get a full list of all the different platforms where you can watch our broadcast, including our 360-degree camera from inside Mission Control. And you will also find on that site a tab that says Watch in Person. That includes a long list of public viewing events across the country. You've got viewing events from here in Los Angeles at Caltech and the California Science Center all the way across the country to New York, in Times Square on the NASDAQ Tower, and all the way into Europe. So please do go to that site if you want to join into a real conversation about landing. Do that, and we look forward to having you back here on Sunday for the news briefing and Monday for landing. And as we go into this Thanksgiving holiday for the in the United States, I just want to wish everyone a very safe and happy Thanksgiving, and thank you again for joining us. We'll see you on Sunday. We're going to play back all the graphics you've seen in the news conference today. Stand by.